Hello, everyone. Come on in. How's it going, Ang? Great thing. Does anyone have any questions before we get started?
I do, Professor. So we have three tests that are due this weekend pretty much until Monday or Tuesday.
Sort of. So you'll notice it says EC sort of. And what that meant is I really think you would benefit from taking the test that I called test 9 or test 9, because it covers these last three chapters in such a way that I think it really well prepares you for the comprehensive final. But it is extra credit in the sense that I'm now dropping your two lowest online tests. So if you don't take it, it's not going to harm you.
Sounds great. Thank you.
No problem. You're welcome. But test 08 is definitely required. That's on chapters 27 and 28. So anything else? So everybody remembers our test will be on, this is Thursday, so you guys will be having a test on Tuesday. I'm going to set it up where you can do it with Respondus Lockdown browser and Respondus Monitor. As long as you have a computer that can access that, do that, and everything, then you can just take it at home. You're supposed to take it during your regular lab meeting time, which I suspect is like 30 minutes after this class is over on Tuesday. But I'll allow you to take it, up to 30 minutes early and no later than maybe 45 minutes late. I don't want you taking any later than that. But as long as you take it during that time period, you should be fine, and you'll get your grade back essentially immediately. Anyone have any questions? Let's see, make sure this is actually working still. I think it is. Yeah, it looks like it is. I had a little bit of stuff left to cover for you guys regarding chapter 31. I sort of gave you a broad outline. I did a derivation, for instance, of the displacement current, which was what Maxwell did to fix Ampere's law. And of course, hopefully it made some sense that it had to be done. But now I need to talk to you about radiation, about the electromagnetic spectrum. To be honest with you, all this is really highly readable, and most of the stuff that I'm going to have you guys do is very much a conceptual type of thing. There's a couple of problems you have to be able to do. For instance, you need to be able to calculate the radiation pressure, and you need to be able to calculate the Poynting vector. And those are just distinct formulas that they gave you. They're really simple. You also should be able to use what I call the baby wave equation, which is velocity equals frequency times wavelength. And then you should know the parts of the electromagnetic spectrum, which I've typed before, but I'm going to type again now. I use this mnemonic in a homage to Rush Limbaugh, who we lost a couple years ago, but I've been listening to him since probably 1988 on television, and then from there on out it was on radio, because his TV session only lasted maybe two or three seasons. But anyways, here's my great mnemonic that I use for remembering the parts of the electromagnetic spectrum. They are great. Notice the capital G, because that's the key first letter of the first word. Excess, notice the spelling of that. Undermines. Various industries. Marxism. Rules. And again, I'm doing that as sort of an homage to Rush, just because Rush used to always claim us teachers were commie pinko bastards. So So I say, as a fan of his, I think I can appreciate that by making a little joke. And of course, he was being somewhat farcical, but somewhat uh, truthful regarding his position on teachers in general. But anyways, I don't mind that phraseology. The main thing is that you know those parts and what they mean. So you should know these parts in order of increasing wavelength. Whoa. Decreasing wavelength in frequency. So I'm doing an abbreviation here. I'm doing IN period for increasing and FREQ for frequency. Well, I guess it's going to go ahead and finish that word for me. Yep, it finishes it every time. Uh, now increasing energy. And you should also know the parts of the visible spectrum, which you guys recognize as Roy G. Biv, but in my mnemonic, the visible portion is from about I think your book's calling it 400 nanometers to 750 nanometers, and it is Vib Gior instead of Roy G. Biv. Okay, so hopefully that helps you guys. You should know those parts, and you should know the wavelengths that end the visible spectrum as spelled out by your book. There are certain questions that can come from that, but like certain things you should know. For instance, what's longer in wavelength? Is it yellow or is it infrared? Is it yellow or is it ultraviolet? Is it radio waves or is it microwaves? That kind of thing. Okay. And there's not a clear and definitive end of each of those areas. So great excess undermines various industries' Marxism rules that hopefully you know is gamma, X-ray, ultraviolet, visible, infrared, microwave and radio, and not a lot. I mean, there's actually a lot of groups that don't consider microwave to be any different from radio waves. So just be aware that sometimes they might not have that M in their electromagnetic spectrum. But that particular version, great excess undermines various industries' Marxism rules, is actually from small wavelength, which corresponds to high energy, which corresponds to high temperature, which corresponds to high frequency. That goes from small wavelength to large wavelength. Okay, so hopefully that helps you out. You do need to know that sort of stuff, and you need to be able to recognize a wave equation and what a wave equation looks like, and what the solution of a wave equation is, and where you can find the velocity for the wave equation. So hopefully all that is pretty straightforward. When we last met, I'm looking at the wrong class right now, so that's not extremely helpful. When we last met, we did the following, and that video has been posted. We got up to the baby wave equation, and I hinted at you the AM 850. You should be able to find that wavelength, that wavelength of 93.7 FM. You should be able to find that one. I did give you the great excess undermines various industries' Marxism rules. I did give you the Vibgyor. I gave you the equations for the electromagnetic radiation, which basically is a vertical, or let's say it's a electric field oscillating in one plane, let's say vertically. That would be called vertically polarized light. It's oscillating in a vertical plane. But light that comes from the sun is randomly polarized. So some of it you get will be vertical, some will be at this angle, some will be at that angle, some will be horizontal. all sorts of stuff like that. Oh, sorry, shouldn't yawn in the middle of that. So all sorts of stuff like that. That's what polarization means. But the other thing is, in addition to, if we're assuming it's vertically polarized, when the electric field is pointing up, then the magnetic field would be pointing to the right, and the radiation would be moving straight ahead. So that's me looking at it from behind. So if I'm sitting behind the waves, what I see is the electric field pointing up right now, the magnetic field pointing this way right now, and the velocity pointing that way right now. They're in that right hand rule sort of way where your index finger is your electric field, your magnetic field is your middle finger, and your thumb is your velocity. So if you use those three like that, that should help you with it. And Maxwell discovering the wave equations allowed him to see that that's what light was. Prior to that, we weren't really sure exactly what was doing the waving with electromagnetic radiation. And at the time, we were convinced that waves could only propagate through matter. So we basically hypothesized the existence of the ether. They call it the luminiferous ether because it allowed light and therefore electromagnetic radiation to go through. But then we did experiments to actually detect that ether, specifically to detect our motion through it. And we basically tried it in like 3 mutually perpendicular directions and got a null result in all cases. And a really wonderful scientist who was sort of Einstein's hero, a guy by the name of Lorentz, worked out a way to save the ether, and they were called the Lorentz transformations. And basically, what he said was that it's as if the ether is doing these mechanical things as you drift through it. And in so doing, you can predict it by using the Lorentz transformations. Now, the neat thing is, Einstein comes along and completely ignores that basically. But looking at electricity and magnetism, and specifically the wave equation that comes out of electricity and magnetism, he saw that there was no way for you to alter the wave equation in the event that you were in a reference frame that's moving with some velocity. So if you imagine the wave equations for an inertial reference frame and you consider going to another inertial reference frame moving at some velocity relative to that last one, sorry, you get no changes with regards to the wave equation. And that basically led him to a lot of paradoxes that he just couldn't see what he called God as making sense of, or making the universe like. So the only conclusion he could reach was that, in fact, the laws of physics are the same for all inertial observers. Again, I've told you about how that's just supposed to be him trying to cut gravity out. And then 2, the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. And that's basically straight out of electricity and magnetism. From that, he was able to predict E equals mc squared. He was able to predict the time dilation and length contraction. And he could actually go back and predict the Lorentz transformations as not something where the ether was being really coy and trying to hide from us, but rather as a direct result of the laws of relativity. So that's how that all played out. Hopefully, after seeing this so many times, you have somewhat of an understanding of it. So I want to reiterate to you exactly what the wave equation is and the baby wave equation. So what I'm going to do is I'm going to open up another document. I needed 242. There it is. And I am going to do that. I'm working on it. Hold on, folks. So now I've got this. I need to duplicate that. And this should be the last one. And this is for 11/30, 2023. So I'm going to type in 30 here in the name and done. And I have that open. Now it looks like someone else has tried to come in. I've let them in. So let's go ahead and share screen so we can make sense of what I've been talking about. Does anybody have any questions on any of that stuff? I just sort of eloquently vomited on you. I know I just sort of threw out a ton of facts in a brief time. So if if you don't understand something or you didn't quite get what I was talking about, please ask me because this is your time. I will be available from now until the Tuesday when you have the exam. Y'all can still text me. That's the most quick way of getting me. So if you text me, but make sure you include your first and last name and exactly what class you're in. You can't even say PHY 242 because I have two of those. You can't say, whatever class you're in. You got to basically tell me whether you're the night class or the day class and what your name is. That way I can reply appropriately. But what we found was the wave equation is this. Whoa, no. Okay, so I'm obviously too far ahead in my. Whoa, how did I even get here? Well, I'm way back here. I'm on page 11 or something. All right. So the wave equation in general, there's a fancy version for 3 dimensions, and it looks like this. And I'll just put a D here, and that's equal to 1 over v squared second partial of d with respect to t squared. That's one way of writing it. But there's other ways as well where you can use a rectangular vector operator. It's literally a box called the D'Alembert. I don't think it's very necessary for you to see that, but if you resign yourself to just looking at one dimension, this vector operator that you see here is an upside down triangle. That's called a gradient, but when you do it this way, you're basically saying, let's apply the gradient to the gradient and then apply that to the field, the vector field D, which might be a vector field, it might be a scalar field. The main thing is it's a field. So if we wanted to talk in just one dimension, then you'd say the second partial of D with respect to x squared is equal to 1 over v squared times the second partial of d with respect to time squared. So that's for anything d that's oscillating. Now, what Maxwell found was that the second partial of the electric field with respect to x squared, and again, he would have said this plus this. This would have been e sub x. This would have been e sub y. And then plus the second partial of e sub z with respect to z squared is equal to mu 0 epsilon 0 second partial of second partial of e with respect to t squared. So in that case, they literally mean you've got to do the e sub x, you got to do the e sub y, you got to do the e sub z, that sort of thing too. That was what Maxwell came up with, and that left-hand side really is what this triangular vector operator represents. Also, he got another one that said the second partial of b sub x with respect to x squared plus the second partial of b sub y with respect to y squared plus the second partial of b sub z with respect to z squared is equal to mu 0 epsilon 0 second partial of b with respect to t squared. So that's the 2 equations he got. I'm doing a little bit of hand waving here because I'd have to take you too far afield in discussing vector calculus to give you an exact representation of what's going on and how I would not necessarily put vector symbols over the e sub x, e sub y, and e sub z. But this is a good enough idea of what you're getting at. Not only that, the important point is you see in the slot where the velocity is, that's not really holding to form. So can anybody tell me, based on these 2 equations, what exactly should the velocity be? I have mentioned it before, so if you remember, that's fine too, but maybe you can figure it out from just looking at this. Anyone? Bueller? Bueller. Nobody knows that? All right. Well, it's got to be in the denominator. The mu zero, epsilon zero are clearly in the numerator, and it's got to be on the same side of the equals as the derivative with respect to time, which the mu zero and epsilon zero are, and it's got to be squared. So hopefully you recognize that the velocity is mu zero epsilon zero square root. So if you take those two numbers, mu zero, which is 4 pi times 10 to the negative seventh, and that's in units of Tesla meters per amp, and epsilon zero, which is 8.85 times 10 to the negative 12th newtons meters squared. Ooh, excuse me, it's newtons. Nope, I forgot I'm doing something else here. Let me change that unit. It's, in fact, coulomb squared per Newton meter squared. Is that right? Nope. Still made a boo-boo. Been a while since I've done it in these units, but if you remember, the epsilon zero is in the bottom of the force, so you've got to have a Newton definitely in the bottom so that it'll come up top. But you also have to have a Coulomb squared in the bottom so it'll cancel out the two charges in the top of the force equation. And then you got to have a meter squared on top so it'll cancel out the R squared in the bottom. So that's the two units. So if you actually multiply those two and then take their square root and then take the reciprocal, you will get C. And the speed of light is now been, so you can take this 4 pi and this 8.85, and you can take as many decimal places as we currently have, which the front cover of your book gives it, and it should give you pretty close to this, which is 299,792, 458, because we've since defined the unit of time and the unit of distance in such a way that this is the speed of light to an infinite number of decimal places in meters per second. It's 299,792,458 meters per second. And like I said, that's to an infinity of decimal places. So if you had, for instance, 9 digits in epsilon zero and 9 digits of 4 pi, if you multiply those two, take the square root of that, and then take the reciprocal of that, you should get 299,792,458 within the experimental uncertainty of 8.85 and the 4 pi. So any questions on that? So this right here is the wave equation. I'm still waiting for questions while I'm talking. And then there's something called the baby wave equation, which I've already told you about, but I'm going to reiterate that. So the baby wave equation, or the kindergarten wave equation, whatever you want to call it. Whoa. Evidently, the software had some strong words for my B. Baby wave equation. Whoa, Nelly. It also has a problem with me spelling the word equation starting with the letter Q instead of E. So the baby wave equation basically can be represented a bunch of different ways. The most normal way is just V is equal to F times lambda, but I'll tell you that it's also V is equal to omega over K. It's also V is equal to wavelength over the period. And in those guys, I got to remind you that omega is 2 pi f, which is also equal to 2 pi over the period. And I've got to tell you that K is 2 pi over the wavelength, so that you can see when you actually divide omega by K, you get the lambda over T. And then if you remember, F is equal to 1 over T. RT is equal to 1 over F, you can get back to the V equals F times lambda. So let me work that problem I just asked you about at the end of last class. what is lambda 850 AM? So there's some things that you got to know about this. I've mentioned it in the past. I think I probably mentioned it last time too. But does anybody recall what the numbers on your radio in your car mean? Like when you turn it to station 93.7, do you know what that means? Or if you put it on AM and it said 850, do you know what that means? Anyone?
I'm assuming it's a frequency.
It is, and more specifically, if you actually listen to radio enough, they've had instances because they're supposed to do it every so often where they do a station identification, and usually those station identifications not only tell you their frequency, but they tell you it in the proper units. And then also some radios actually have the units on it. So does anybody remember what the units are for FM or for AM for that matter? Just blurt it out if you think you know it.
Is it hertz?
Hertz is definitely the unit of frequency, but these are a lot bigger than hertz. So I'm going to write it right here and go ahead and blurt it if you think you know it. But when they say 850 AM, what they mean is the frequency is equal to 850 kilohertz and it's amplitude modulated. So that's what the AM part means. I'll make this, well, I was trying to make that D a little thicker. That did not work out like I planned. But it now looks really mutilated, so that's helpful. Modulated. Okay. And then when I say something like, what is the wavelength of 93.7 FM? There's a similar part that is useful. Anybody know this frequency unit? In this case, it's F is equal to 93.7 and it's megahertz. And FM means frequency modulated. And your book has some decent pictures of frequency modulation and amplitude modulation. So I will share those with you, or you can just look. They're actually in, trying to remember what section they showed them in. It was probably section 31-6 or something like that. Let me double check. No, maybe it was, well, it might be because that's 31-5-1. This is definitely not here. One more check, 31.7. Not there. 31.8, not there. So maybe it was before that. Anyways, there is definitely a section in there. And when you see amplitude modulated, what normally looks like a sine wave would be like this, where it goes up to the max height, down to the minimum, to the max height in the negative direction, back to that same height, back to that same height, like that. So if it looks like this, it's not amplitude modulated. An amplitude modulated wave would have sort of a little envelope around that sine wave that makes the sine wave sometimes short like this and sometimes tall like that. That's what amplitude modulation looks like. Frequency modulation will have the same height from, say, here to here, but sometimes you'll get the lines going really quick, several up and downs in one little spot, and then slow up and down for a little while, and then a fast up and down for a while. That's frequency modulated. So you can find those pictures in your book if you'd like. The main thing is that's what they are. And it's literally, if you want to, for instance, send out radio waves from a radio station, you first have to create an antenna, and the antenna is going to send out waves, and those waves have to have the wavelength and frequency corresponding to the radio station that you're in. So the government actually gives a certain number of people certain wavelengths, and they give them a specific range from, this wavelength to that wavelength, or from this frequency to that frequency, and that's the only place you're allowed to be in. You'd have to send out waves on that, but you also want the radio signal. So that wave's just called a carrier wave. And if you're on an AM band, then that means you're going to have a multiplication factor. Instead of having a times the cosine omega t plus, or kx minus omega t, instead of having just a constant in front of it, you're going to have a function of time in front of it, and that's going to make your amplitude modulated. If you're frequency modulated, then you're going to have some constant a in front of the cosine of kx minus omega t, but the omega part is going to be a function of time, and that would be the frequency modulation. So hopefully that gives you a little bit of a background on it. Let's see. There is a wonderful problem. Well, actually, let me go ahead and solve this one first. So we know that V is equal to F times lambda, or lambda times F. In this case, we're actually wanting lambda. So lambda 850 is going to be equal to the velocity divided by the frequency. Now, here's the trick. I only gave you one piece of information, but remember, I also gave you great excess undermines various industries, Marxism rules, and these are radio waves. So it's one of these types of radiation, which is called electromagnetic radiation. So it travels at the speed of light. So you're going to write in 3.00 times 10 to the 8th meters per second for the velocity. And then you're going to have to divide that by the frequency, which is 850 times 10 to the 3rd hertz. Remember, a kilohertz means 10 to the 3rd, so that's where that came from. And this gives me on the order of 352 meters. That's really, really, really long. That's like 4 football fields, okay, including end zones. And not only is that really, really long, but imagine a wave that extends one peak at the back end of an end zone of a football field. You go across the end zone, then you go across the 100 yards, and you go across the next end zone, then you go across another football field and another football field and another football field, and right around there you find the next peak. That's how long this wave is. And not only that, 850,000 of them pass through you every second. So that's a pretty remarkable thing about the speed of light and how fast it is. 850,000 of them pass through you every second. Now we're going to do the wavelength of the FM station. So velocity equals frequency times wavelength again. This is still a radio wave, so we know lambda 93.7 is equal to 3.00 times 10 to the 8th meters per second. That's going to be divided by 93.7, but in this case it's megahertz, so you got to say times 10 to the 6 hertz. When you do this math, I think this one turns out to be 3.201. Let me double check. 3 e to the 8th divided by 93.7 e to the 6th, and that gives me, yes, 3.202 meters. So, that's on the order of the height of a basketball goal, say the rim of a basketball goal. So that's the wavelength. Of course, if you're talking about any other kind of wave other than electromagnetic radiation, then you don't necessarily know the speed unless they give it to you, or unless they give you a formula for the speed. So for instance, the speed of a wave on a string is the square root of the tension in the string divided by the mass per unit length of the string. Or the speed of a wave going through a metal rod is the square root of the elastic modulus of the rod divided by the density of the metal that the rod's made of. Or if you're wanting to know the speed of a wave through a fluid, then it's the square root of the bulk modulus of the fluid divided by the density of the fluid. That's actually why, for instance, we say sound when you're scuba diving is omnipresent or omnidirectional. So for instance, if I'm scuba diving with a friend and maybe they see something that's kind of scary or something cool that they want to show me, what they generally do is they either take their dive knife or a wrench or a hammer or something they keep on them that's metallic, and they bang their scuba tank, and I'll hear a knock, knock, knock or something like that. However, I'll hear it coming from every possible direction. The reason why is the velocity of sound in water is quite a bit faster than the velocity of sound in air. So your brain's not designed, quote unquote, designed for that. What normally allows your brain to decide from which direction a sound comes is the difference in timing in the left ear and the right ear, as well as some, experience and stuff like that. But the speed is so fast, there's too small of a time interval between the sound arriving at the right ear and the left ear, so your brain can't tell anything. It just thinks the sound's coming from everywhere. So that's why those velocities tend to be so high. All right, now that we've got the baby wave equation, you know how to use that. I wanted to work a very specific type of problem regarding EM waves. So let's do this. Assume let's say 500 hertz, and I'm going to put a decimal after that so we can pretend like it's 3 sig figs. So assume a 500 hertz EM wave is traveling in the Z direction. And let's say the positive Z direction. Actually, let's don't say the positive Z. I can make it up that way where it will be up to you to figure out whether it's a positive or negative Z. So I can change it right now on the fly, but it's in the Z direction. We don't know if it's positive or negative. So I'll put positive or negative question mark. Okay. It's moving in the positive X direction. And, better make sure I get it right. And E points in the X direction. Such that the the amplitude of the electric field is 2.00 volts per meter. And they want us to, let's say, write expressions, vector expressions for E and B as functions of position and time. In other words, it's going to have an X, a Y, or a Z in it for position, and it's going to have a T in it as well for time. So what we have here is a frequency. So we know, for instance, solution. We know the frequency is equal to 500 point hertz, which means 3 sig figs. We also know that in general, the electric field, in general, the electric field should have a form something like this. E0 sine kx minus omega t, or it might have E0 sine kz plus omega t, or it might have E0 sine ky minus omega t in all other possible ways as well. And not only that, the E should be a vector that points in the direction that the magnetic or that the electric field is oscillating. So if it's vertically polarized and you called vertical direction the Z direction, then it would be times the K hat. And the magnetic field would be the same sort of scenario. It would be B0 sine kx minus omega t equals r dot dot dot. So in other words, the exact same thing could be said about that. So we've got to sift through this and figure out exactly what is omega, what is k, whether it's kx minus omega t, whether it's kz plus omega t, kx plus omega t, kz minus omega t, ky minus omega t, ky plus omega t, all that stuff. So we know the frequency is 500 hertz. We also know omega is equal to 2 pi f. So I can go ahead and calculate that. And I get 3,142. So this is going to be 3,142, and that's in radians per second. Now, we also know that the velocity is equal to the speed of light, and that's equal to omega over k. Or you could use the lambda times f, whichever you want, but we need k, so why not go ahead and solve for that? So I'm going to use the v equals omega over k to find that k is equal to omega over the speed of light. So I'm going to say 3,142 radians per second divided by 299,792,458. Now I really, since I'm using 4 sig figs on this omega, then I need at least 4 sig figs on the speed of light. So I just went ahead and wrote everything. There was really no need to write more than 4 sig figs, but I did. Okay. So I'm going to take this 3142, and actually I've taken the whole number that the calculator gave me, which was 3141.59. That's what it actually gave me because I used pi to 3.14159. So that's what it actually gave me. And then, of course, that means the last 3 digits are meaningless. But when I take this number and I divide it by 299,792,458, I get k is equal to 1.048. That's 1 extra sig fig times 10 to the negative 5th. And if you look at these units, you'll see that it's radians per second times seconds per meter. So it's just reciprocal meters. And that's what the units of k are supposed to be. So we've got some key parameters here. But what I need to know is it says, assume a 500 hertz electromagnetic wave is traveling in the z direction. Okay. So that means it's traveling in the z direction. So we should have z direction implies you should have k z minus omega t or k z plus omega t. Okay. We're not really given that. I'm going to go on the assumption that it's kz minus omega t because it normally is. When someone says the z direction, they generally mean in a positive z direction. But we'll address that a little later if we want to get into specifics. So now what I'm going to say is by going in the z direction, that means the thing that's going to make the electric field oscillate up and down, you know, from 0 to pi, or excuse me, from 0 to 1 to 0 to negative 1 to 0 again, you know, after the argument becomes 0 and then pi over 2 and then pi and then 3 pi over 2 and then 2 pi. That's all going to happen along the z-axis. That's why I had to write kz there. So now I can say E, oops, I should probably stick to the blue. I can say E and I'll put a vector symbol on it, is equal to 2.00 volts per meter. Now it says the wave is traveling in the z direction, so that gives me what k should be multiplied by, and E points in the x direction. So if I go on the same assumption I did before, which said z direction means positive z direction, then I should probably say x direction means positive x direction, in which case I'd write an I hat in front of it. Okay, so that means the electric field will be oscillating left and right in the x direction. Okay, so I've got that. Now I'm going to multiply that by sine of, and now we're going to use k, which was 1.048 times 10 to the negative fifth meters to the negative 1 power times z. And again, I'm going on the assumption that it's moving in the positive z direction, so I put a minus there. And now I'm going to say 3,142, and that's radians per second times t. That's my electric field. Okay, but both of these assume at t equals 0, E points in positive x direction, and then moves in positive z direction. So I'm going with that as if that's the assumption right now, and I need to follow it. So what I'm going to do is draw a little coordinate system over here so I can keep my wits about me. I'm going to say, let's say that z will be to the right. So there's my z-axis. And I am going to say that x points upward and that y points out of the page. Notice that is a right-handed coordinate system. X is your index finger, Y is your middle finger, and your thumb is Z. And you can see that that actually works. So that is a right-handed coordinate system. And what we just did was we forced the electric field to oscillate back and forth in the positive and negative E direction, or excuse me, positive and negative X direction. So I'll say it looks like this. Oscillating that way. Okay. And in fact, its velocity, they said, was moving in the z direction. And we went on the assumption that that meant v was in the positive z direction. So that would be the v direction. And what I mean with this is right here, the electric field is pointing up. Right here, it's pointing up. Right here, it's pointing up. Right here, it's pointing down, 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 up, 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 down, 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 like that. Now, what we know, because the pointing vector, so S is the pointing vector, and that's 1 over mu 0 E cross B. That's called the pointing vector. And that is the energy delivered by a electromagnetic radiation per second per square meter. So this is in units of joules per second per square meter. And that's what you use if you want to find out how much energy is being delivered, for instance, from the sun, which I told you last time would be about 1,350 watts per square meter at the upper edges of our atmosphere. Again, assuming I remembered that correctly, that 1,350 was the figure for the outside of the atmosphere. It's a little bit less, of course, once you get to the surface, again, assuming I remembered that correctly. So we've got that, and because we have S equals 1 over mu 0 E cross B, that's why I know that when you take E cross B, the cross product has to point in the direction of your thumb, which has to be the velocity. Okay, because the Poynting vector has to travel in the direction that the electromagnetic radiation goes, or else it's not delivering it that way. So I have to orient my hand like this for the diagram I just drew, and I see that my middle finger is pointing towards me, which means that my magnetic field should actually point out of the page. So now I'm going to draw the magnetic field, and I'm going to draw that in, let's say, black. So I've got the electric field up right now. That's why I chose my index finger pointing up. My middle finger is pointing towards me, and my thumb is pointing to the right because that's the direction of velocity. So that means at least while the E field is up, the magnetic field has to be out of the page like this, and then in the page, and then out of the page, and then in the page. So in this case, it's like that. So that's your B. The blue is your electric field, like that. And now that I've got that worked out, I can write exactly what the B field is. So we've already gotten this electric field, which I'll circle or box off in red so we know it's a done deal. Now, the nature of the electric field, according to the wave equation and Maxwell's equations, there's more work you got to do with Maxwell's equations to see this. But what you discover is that the electric and magnetic fields are in phase. So they have the same kx minus omega t, and they're not displaced one way or the other from the other one. So there's no phase angle difference between them. So I can now say that the magnetic field B should equal some B0. We can obviously tell that when the electric field points in the positive direction, the magnetic field should point in the positive Y direction. So I'm going to put a J hat right here, and I'm going to leave the space here for the magnitude of the electric field, which I got to figure out in a second. But this is going to be sine of, now I'm going to do the exact same argument that I did for the electric field. So that's 1.048 times 10 to the negative fifth meters to the negative 1 power times Z minus 3142 radians per second times T, and that's that way. So how do we actually figure out exactly what the electric field, or excuse me, the magnetic field is? Well, there's this other result that helps us out. Specifically, you can sort of get it from the wave equation, and what it basically says is that B0 over E0 is equal to 1 over C, or E over B is equal to C. That's the easier way to say it. So the other thing I know is E0 over B0 is equal to C. So that's just another equation you should definitely commit to memory. So I'll underline it here just to say it's important. So that tells us that the magnitude of B0, or the magnitude of the magnetic field, which is B0, is going to be equal to 2 volts per meter divided by C. So if I take 2 and divide it by, let's say 299792458, I get 6.671 times 10 to the negative 9th. And it turns out that a volt second per meter squared is actually a Tesla. Once I have that down, then I can go ahead and write exactly what the magnetic field is. So obviously this number is a lot bigger than I had planned. So I'm going to write it and move the thing a little bit. So it's 6.671 times 10 to the negative 9th Tesla. And that's the electric field, or excuse me, the magnetic field. Any questions on that one? So this is exactly the kind of thing that I expect you to be able to do. I also expect you to be able to be given an E like this and a B like this, or just an E like this, and you should immediately be able to tell me what the wavelength is, what the frequency is, what the period is, what the amplitude is, what the strength of the electric field is, what the strength of the magnetic field is. All that stuff is fair game, but that should be what you're should be able to do. Now, one thing I'll mention, and your book did this too, is notice that the magnetic field is on the order of nanoteslas. For starters, a Tesla is a big magnetic field, so it's a big magnetic field strength. So that's one issue, and basically all of this is because of the units. If you actually were to calculate the energy coming in this electromagnetic wave, what you would find is that the energy from the electric field is exactly the same as the energy from the magnetic field, even though the magnetic field is weaker than the electric field in volts per meter versus Tesla. In fact, there's an entirely different set of units that you might encounter in which the electric field and the magnetic field sometimes have exactly the same unit, but other units have them that have a different unit, but they still have about the same size. So just keep that in mind. Does anybody have any questions on that particular example? So that's probably the single most comprehensive example of the stuff you need to be able to do from this chapter, is be able to write out the electric field, the magnetic field given a description like this, and also be able to use the baby wave equation for electromagnetic radiation if you're just given wavelength or frequency. But if you're dealt with some other kind of wave that isn't electromagnetic radiation, then you have to be given two quantities, like the velocity and the frequency, or the velocity and the wavelength, or the wavelength and the frequency. Any questions on that? All right. Your book does take the time to do a derivation of the wave equation. I like that derivation. It's fun. By all means, check it out. You can also go on my webpage, on my YouTube channel, and you will see a derivation of Maxwell's wave equation, sort of a more vector calculus sort of way if you want to, but you can check that out as well. You can also look in figure 3112, and it has the parts of the electromagnetic spectrum. So I'll tell you that parts of the EM spectrum are in figure 31-12. So I definitely recommend you look at it, but you can see, in fact, that they put that in the opposite order of what I did. My order is great excess undermines various industries, Marxism rules. Their order is rules, Marxism, industries, various undermines Marxism, or excuse me, X-rays, it's excess, and then great. Sorry, I was trying to remember the words in opposite order. I'm not as good at that as I thought I might be. The cool thing about it is you do see that in the microwave to the radio area, the first thing you hit in going from visible light towards radio waves is you first hit satellite TV, then you hit cell phones, and at least on this diagram, it shows you two different cell phone frequencies. Then you hit TV, which is channel 7 and up, and then you hit FM radio, and then you hit TV, which is channels 2 through 6, and then there's a big gap, and you hit AM. Okay. And in between that AM, a lot of that's communication stuff that our military uses and some other groups use as well. But yeah, basically, just about every bit of that spectrum has been spoken for in the U.S. and various other countries. But I think that's about it. Let me see if I see anything else jumping out at me. So they do some stuff like calculate the wavelength of a 60 hertz EM wave, calculate the wavelength of a 93.3 megahertz FM wave, calculate the wavelength of red light from a laser. Those are just simple equations, just like are using the baby wave equation, just like we did with the AM 850 and 93.7 FM. So it's just a matter of, you got to realize those three types of radiation, or those three types of waves, are EM radiation. Therefore, you know their speed is the speed of light, and then they gave you the frequency, so you just solve for the wavelength. So that's something you should definitely be able to do. So I'll say be able to do like example. I'll say examples 31-3. Let's see if there's any more that jump out. Oh yeah, 31-4. That one's one where they say an antenna of a cell phone is often a quarter wavelength long. That's a typical type of antenna. There's also a half wavelength antenna, so on and so forth. But anyways, they say the antenna of a cell phone is often a quarter wavelength long. A particular cell phone has an 8.5 centimeter long straight rod for its antenna. Estimate the operating frequency for the cell phone, and from that you end up getting 880 megahertz, which is pretty close to what we actually use as one of ours. So that's a worthwhile example. They ask you to estimate the phone call time lag for both a continental underground cable, so an intercontinental underground cable that runs, say, from New York to London. That's on the order of I don't know, about 4,000 or 5,000 miles, and yeah, about 5,000 miles. Or they also say estimate the lag time if it's a satellite call, in which case the satellite is up some 36,000 kilometers above the surface of the ocean. So you're going to shoot a beam of electromagnetic radiation from the Earth up to a satellite, and then it's going to bounce back down from the satellite and come back down to Earth, say in London or something. And what you'll see is satellite is actually quite a bit slower, and there's quite a bit of lag. That's why you see so much confusion with communications when you're watching satellite links on the news. So that's a good example. I wouldn't necessarily put that down as one I definitely say you need to know how to do, but I would say it would be bad if you didn't know how to do it. So I'll just leave you with that. There's 31-3 and -4. Let's see if there's any other ones that jump out at me. The measuring the speed of light with the Michelson, and they did some other ways too, but that's not necessarily that important. But definitely the Poynting vector is important. So the Poynting vector is S is equal to 1 over mu 0 E cross B. And of course, the magnitude is sometimes all you need, because they're just wanting you to calculate basically how much energy per unit time per unit area. So what I would tell you is that S is equal to 1 over the area times du over dt. And that ends up giving you a magnitude that you could write as epsilon 0 c times e squared. But you could also write it as c times b squared over mu 0. But you can also write it as 1 over mu 0 e times b. So those are all different ways you could actually write the magnitude of the Poynting vector. But the main thing is you're seeing that it would have units of joules per second square meter, which is the same thing as joules per second per square meter. Okay. I did tell you that the Earth's, I just double checked for you guys. It does say radiation from the sun reaches the Earth above the atmosphere with an intensity of about 1,350 joules per second per square meter. So I would say S for the sun is equal to 1,350. And you can either say this is watts per square meter, or you could say it's 1,350 joules per second per square meter, or you could say it as 1,350 joules per second meter squared. All of those mean the same thing. So that's like example 6. So I'll put that one down there. The 5 wasn't bad, but yeah, I think the 4 was the cell phone thing, so that wasn't too bad. I'm looking at this, seeing if there's anything else. Oh yeah, radiation pressure. So the other thing is radiation pressure. Radiation pressure, which we could call delta P, is actually equal to, if it's fully absorbed, it's delta U over C. So that says fully absorbed. So that's like the photons bombarding a black surface. The black surface, being a black body, is going to completely absorb the radiation. And because the irradiation was moving perpendicular to the black surface, now the black surface is going to move a little bit in the direction of the radiation. That's what we mean. But just like we did when we were studying particles bouncing off the walls of a container when we were deriving the ideal gas law, we found that in that case, the pressure was actually twice delta U over C, and that's when it bounces off. So this is radiation. Oops. This is radiation fully reflected. In other words, the surface, which might have been white, for instance, not only did the light bounce off of it and the white surface stop it, but the white surface hit it so hard that it bounced it back with the same speed that it came in at. That's what it means by fully reflected. So if you go and try to calculate what that means, you end up getting that the pressure is actually equal to the average of the Poynting vector divided by the speed of light, and that's fully absorbed, or it's equal to 2 times the average of the Poynting vector divided by C, and that one's fully reflected. So those are the two equations you need to know for this. I was giving you the definition when I said delta U over C, delta U over C, but here is the actual result that you'll use. So for instance, people have postulated making a spaceship that can use the radiation pressure from the sun and make a solar sail. And you find that that pressure is not that big, but the point is, if you have a big enough area, then force is equal to pressure times area. Could be pretty significant. But even if it's small, if you get it for a long time, if you actually allow a small force to be applied constantly for a long period of time, you can get quite a bit of acceleration. So that's a worthwhile thing. I will say we need to include now example 7, which again, all these are really, really super, super easy. And example 8. So I think that's about it. There was something else I thought I wanted to talk to you about, but I can't remember. They do talk about Marconi. Oh yeah, that's where they're showing the amplitude modulation and frequency modulated. Let's say C figures 3118 and 3119 for AM and FM. So that talks a little bit about Marconi, so you'll know what he did historically in case you ever appear on the on Jeopardy or something like that. Tuning a station, they give you some information about that. That's pretty much just like the other example, so I'm not even going to list that as another one. They list other different versions of communications like cell phones, remote controls, Wi-Fi, Bluetooth, all that kind of stuff. So he actually gives you a good amount of information about how the world works. For instance, how do we know that the moon is moving away from us on a daily basis and stuff like that? So we've done just about everything. I'm still trying to remember what it was that I wanted to mention to you guys. I think I've got everything, but there was something else that's bothering me. I'll look back in the earlier sections. We found the speed, we found the wave equation. Oh, I remember what it was. I was going to advise you guys, or actually I was going to work an example like this for these guys, for you all, is I was going to show you what they did in section 31.4. Subsection 31.4. Where they actually talk about radiation and they show you how the waves form. I want you to understand that, but I'm not sure you necessarily will from one presentation. But I definitely read it if I were you and try to make sense of why you're getting radiation that looks like this figure that I drew back here. This figure that I drew down here in the bottom left, that is a result of that discussion that we'd had in section 31-4. And then they talk about far field and near field and all that good stuff. That's pretty relevant. But they also work an example with Ampere's equation. And I think I did work that for you in section 31-2. They did that example at the very end using the displacement current. I was going to tell you to know that one, but I'm not going to ask you that on a question. But I definitely think it's cool to see it done. So you can look at example 31.1 yourself. I think I already did it for you guys, but like I said, I'm not going to ask you to do that on the final. So just keep that in mind. You don't have to do it, but this is a pretty good synopsis of everything you have to do. You guys are of course free to go. I hope y'all have a good weekend studying stuff. Keep an eye on your email in case I decide to make some videos that might be helpful to you. Sometimes I do stuff like that just to, work out some difficulties that students are having based on emails or text messages they sent me. So you're free to go. I'm going to wait for the last person to leave before I leave. Have a good weekend. Stay safe, and let's get prepared for your exam so you can kick butt on Tuesday.
Thank you, Professor Younger. And I have a quick question.
Yeah, go for it.
So is tomorrow, are you going to update everything to like show what our lecture grade is?
Yeah,
before we take
I
the
was
final?
hoping to have it done by today, but I discovered there was like 4 training things that I was supposed to do. But they're due tonight, so I didn't want to wait till the last minute.
Right.
So they should be done. It should definitely be done tomorrow, and I'll email y'all when they are done. But yeah, all that'll be fixed, including your test grades and including some adjustments on homeworks and stuff of that sort.
Okay, awesome. And then there's also 2 practice tests for the final. Is it supposed to be that way? Like 2 different questions or something? Or
It
set of questions?
shouldn't be. No. Let me double check what I've got up here. I've got Oh, I see. 242 final. Yeah, it looks like I just copied it twice. I'll turn off one of them.
Okay, sweet.
Okay, yeah, that should do it. Yeah, they should be identical. So hopefully that's fine. Let me know by text if y'all have any problems with it, like if it's missing questions or something weird like that. Let me know by text, and don't forget to tell me what class you're in so I can check the right one.
Okay,
And
awesome.
sorry I
Thank you.
didn't see your chat there, John.
Oh, it's all good. All right. You have a great weekend, Professor Younger.
You too. I've enjoyed having you guys.
All right. Thank you. Bye.
Bye-bye. Tony, Randall, Julia, Taylor, anybody else have any questions?
Hey, Professor, real quick. When I look at my grades, it shows that there's like a lab 8 and lab 9. I had no idea what those things are about.
Yeah, they shouldn't be in there at all because you're an online class. What it is sometimes when I copy stuff over from old courses from previous semesters, it pulls in assignments from those previous semesters. So you got stuck with something that's there, and I haven't quite figured out how to remove it. So it will not count against you or for you at all. Hopefully, I'll find a way to completely get it out of the grade book by tomorrow.
Sounds good. Thank you. Have a great
Okay.
weekend.
You too. Don't worry, guys. I do actually do a hand calculation. Like I'll grab 3 or 4 students at random and I do a hand calculation of their grade and compare it to what Canvas is doing. And then I also compare it to what an Excel program I write is doing. So when it's all said and done, your stuff is checked out pretty thoroughly. Thanks again, everybody. Anybody
Mm.
else? Randall?
Yeah, so the final, like in terms of like what chapters it's on, I'm sure it probably covers the chapters after like the midterm for the most part. Like of course, like it's still gonna have stuff from before it, but
It's the actual final is completely comprehensive. So it's going to be, I'll type it right here. It's chapters. Let me double check. I think we started with 17. So it should be 17 to 31. Anything outside of that is extra credit. Actually, I can double check on that 16. Hold on
Because
while you're here.
honestly,
Go
I
ahead.
am still struggling my way through chapter 30 at the moment. I haven't even got to 31 in terms of like doing the homework and stuff. So
You're not bad off. Like I said, there's a very limited amount of stuff that comes from 31. That's why I sort of rushed through that today, is just to show you those little things that you got to be able to do. But yeah, it does not include 16. 16 was a chapter on sound, so it's 17 through 31. Uh, if you actually take the time to try to take that test 9 that I put up there, you'll get a lot more experience with 31 and a lot more relevant experience with 31. So you'll know exactly what 30 and 31 are about, because they're not as hard as they seem.
would you say that like the questions are going to be kind of evenly distributed between the chapters, or do you think it's going to be more weighted towards these more recent chapters?
My attempt is usually to make it about even. I'd have just as many from 17 as I have from 31, but sometimes I do err on the side of the most recent stuff because that's supposed to help people more. But like I said, I try to avoid that because sometimes I find out that students really had a hard time at the end and I didn't realize it. So
Yeah, ever since we got into electricity, I've been struggling, which I guess is good for me because I decided to do. I'm going into mechanical engineering, so
well, I'll tell you, when I took physics,
not
the
electrical.
electricity part killed me too. And it was like, it just came together on the final. So don't lose faith. You might actually get it anyways.
Yeah, we'll see. Anyway, have a good one, Professor.
Thanks, Taylor. You too. Jalea, did you have a question? All right. I'm not sure she's still here. So I think I'm going to go ahead and stop sharing. And I'm going to tell everybody to have a good day. Looks like it's just me and Jalea still in here, but I don't think she's here. Actually, I think, yeah, it doesn't seem to be. Bye, everybody. Thanks for coming. Enjoyed seeing you. Ignore that mess back there. Don't tell room raiders. Bye-bye.